Last year, the James Webb Space Telescope began producing stunning images of the universe. It faces away from the sun to reduce the impact of strong light. It turns its giant golden reflector toward the universe. Past the light it collects to the low-temperature sensor. Looking back at the light emitted by the early universe 13.5 billion years ago, this is an incredible human achievement. But if we create a giant radio space telescope, we can go back even further, detecting signals emitted by hydrogen atoms in the primordial universe. This is light that even the James Webb Telescope cannot detect. However, radio telescopes are bulky and, even on Earth, establishing such a large collection area is a challenge. Arecibo, the largest radio telescope in the United States, will close in 2020 after 57 years of use. The wall collapsed due to two support cables breaking. The telescope utilizes a natural crater to shape and support a spherical reflecting surface. Radar waves from the distant past are blocked by our atmosphere. But if we could build something like this in space, use naturally occurring craters, just like Arecibo used gas sinkholes. This is exactly the plan proposed by NASA scientists. Radio telescope on the far side of the moon, marked by the numerous craters on its surface. It will be the largest space telescope ever built, and employing clever engineering, it could cost much less than a thin telescope. This is its story. The basic concept of large radio telescopes is not new. Arecibo Observatory in Puerto Rico. It is a huge, stacked antenna dish with a diameter of 300 meters. But this lunar telescope will be bigger. Engineers on the project will be able to combine a telescope with a diameter of 50 meters larger than the Arecibo telescope. Antenna dish suspended in huge crater. This proposal is an NAS initiative. So how feasible is this? Building buildings on the moon is not easy. The core idea behind the telescope is to use craters on the moon as a base. No need for heavy support structures. And use the metal mesh that naturally blows down under the gravity of the moon to build a reflective disk. The use of network cables greatly reduces the weight of the system, while still allowing radio waves to reflect off the flag. As long as the gaps in the grid are shorter than the wavelength of the incoming signal, the wave will bounce. In order to achieve this goal, we need to find the perfect crater. Since 2009, scientists have been scouring data obtained from the Lunar Reconnaissance Orbiter. First, it needs to be on the far side of the moon, because the moon is tidally locked to the Earth. The far side of the moon always faces away from the Earth, so it blocks the radio noise we emit. The farther the crater is from the near side of the moon, the better. To accommodate the 350-meter wide plate, the crater circumference needs to be 5 kilometers, 175 meters deep. It needs to be as smooth as possible. There aren't any big rocks or mounds. The edges must also be as level as possible. To easily secure hanging wires, we want to point far away from the center of the Milky Way. To observe radio waves emitted by the early universe, we need to point telescopes to quieter parts of the universe. But we can't point out the crater. We must rely on the natural movement of the moon to sweep across a portion of the sky. This tracking scan changes depending on the north and south positions of the crater. By selecting craters between 10 and 20 degrees further north latitude, telescopes can avoid noise from the Milky Way. These criteria narrowed the options from 82,000 craters on the far side of the moon to 300. From these 300 craters, 50 were selected for closer consideration. The crater finally selected is located at 10 degrees north latitude. Building a giant telescope on the moon is the biggest challenge facing the project. The telescope will focus on capturing information on the electronic spectrum between 7 MHz and 47 MHz. This corresponds to wavelengths between 6.4 and 64 meters. This leads to the first engineering design limitation. The dish needs to reflect and focus these waves. On Earth, mass is not a huge limitation for fixed structures. However, transporting these materials from Earth consumes huge resources. Therefore, we want to reduce the weight as much as possible. We can use lightweight carbon fiber cables to form support structures. When the temperature on the moon fluctuates dramatically during the day and night cycle from -170 degrees Celsius to 120 degrees Celsius. In degrees Celsius, the material also helps maintain the shape of the structure. Temperature fluctuations cause aluminum materials to expand and contract, thereby distorting the shape. These carbon fiber wires will then be fixed to the sides of the crater. The natural droop of the wire forms a support structure. However, hanging wires naturally form a catenary shape. This is not suitable for use as a concave mirror. We need to create a device that can focus the reflected electromagnetic waves. The shape given to the interior of the ring mountain, where we can hang the receiver. To get a better focused beam, the shape must be closer to a semicircle. But how do we achieve this using a wire with only 2 hairy spots? This is where things get interesting. This kind of wire has no compressive strength. Must be hung under pure tension. Hang a thread from a point. It will hang vertically downward. Hang it between 2 points. It will sag downward until the entire rope is under tension again. But if we could apply more weight, it will sag. Creates a deeper parabolic arch. To maintain tension, we can take advantage of this. Strategically hang weights along the length of the Enterprise to change its shape. But anchoring it to the edge of the ring is easier said than done, especially if we're going to build it without the help of astronauts. Thankfully, the moon's gravity is weak. Make things easier. The moon's gravity is about 16% of Earth's. Supporting a 2,000-kilogram telescope on the moon is equivalent to supporting a 320-kilogram weight on Earth. The question is, how do we deploy them? One plan involves using a 2-axis robot currently under development at the time of the jet propulsion trials. Manually drag wires into place. Another plan is to create an anchor lock shape above the crater before landing, either by launching an anchor from the lander before landing, either by landing multiple landers at their anchor points. The least labor-intensive option, however, is to use a single lunar lander. The lander will land in the center of the crater and launch an anchor above the crater rim. These hairs are similar to boat hair, and when stretched taut, they extend into the lunar regolith. However, the weathered surface of the moon is very sharp and requires great care. To minimize friction between the rope and the ground, depending on the type of tongue hair, extensive testing and validation is required to ensure its reliability and prevent any potential failures. This is a very difficult thing to simulate. This is highly dependent on the topography of the site. On the other hand, relying solely on projectile anchors significantly reduces cost and complexity. The total estimated cost is $2.4 billion. It is estimated that deploying circuits for the lunar rover will cost $4.5 billion. This compares to a cost of $10 billion for the tiny telescope. Once deployed, these anchor points become the stock prices on which the rest of the structure is built. Start by raising the antenna receiver to the focal point of the structure. If deployed by a separate robot anchor, tightening of these receiving devices can be accomplished from the anchor point, but this in turn pulls the thread along the machine-worn layer of desired differentiation. Ideally, robotic pulley systems could climb existing anchor valley lines and deploy these structures without causing any more friction on the crater rim. Next is the reflective mesh. The net is made of ultralight reflective material, such as plated wood. To deploy the reflector, pull the guide wire to the top of the yarn. The wool in turn unfolds the wire mesh. This inspiration comes from origami. This concept has been demonstrated on several space missions. From solar arrays to heat shields, there are good reasons. The intricate folding patterns of origami machines allow engineers to fit large structures into the space that the machine can download. This is the perfect solution to fit a 350-meter wide radar antenna into a lunar lander with limited space. Once deployed, the radio telescope can begin sending data back to Earth. This telescope won't give us pretty images like a microwave telescope, but it will give us data about how hydrogen is distributed in the universe. But what's the use? It will give us new insights into the formation of the universe. The main assumption currently is that the hydrogen distribution should be uniform in space and time. Scientists estimate that this uniformity assumption also applies to the cosmic background radiation. But this needs to be verified by practical testing, and not just at the theoretical level. This telescope will be able to detect these hydrogen. But how to detect it? In the early universe, there is no light before stars begin to form. But there are hydrogen atoms. Lots of hydrogen atoms. Cold interstellar hydrogen is at the lowest possible energy level and does not radiate anything, however. Sometimes these atoms can pass through collisions with other atomic particles and be excited to a higher energy state. At some point, by natural decay or by secondary collisions, this energy needs to be radiated out again. Energy is released through photons of specific wavelengths. By listening to the unlimited radio waves at this specific frequency, we can quantify hydrogen stars throughout the universe. But our goal is not just to collect signals at a certain point in time. Instead, we track these formations over time. Because of the redshift, we can do this. As the universe expands, it stretches the frequencies lower and lower. We can determine the age of a signal by the extent to which it shifts to longer wavelengths. This data is critical to refining our models of the conditions that lead to star formation, and provide insights into how the universe gradually cooled after the Big Bang. Of course, the telescope needs to send data back to Earth. This is where the telescope might benefit from other lunar missions. When the Apollo astronauts ventured to the far side of the moon, they can't communicate with Earth. Things have improved since then. My country's first and only lunar far-side communications intermediate satellite launched in 2018. The satellite is parked at the Earth-Moon Neuer-Lagrange point and is communicating with the lunar lander. It became the first lunar lander to soft land on the far side of the moon. NASA and ESA will need to allocate significant resources to this mission operation. In particular, the Artemis program aims to send humans to the south pole of the moon. The program will be fully rolled out over the next decade. As the number of lunar missions increases, communication between the moon and the Earth will become more convenient and efficient. The cleaning and testing mission itself is only planned to run for 1 year. Scientists believe they can collect enough data during that time to deduce the evolution of the early universe. Of course, the capabilities of large radio telescopes come from more than just detecting early clear spacecraft. The long radio wave spectrum is full of other useful information. When radio waves pass through magnetic fields, they are split and changed. Radio telescopes can use this to detect the magnetic field of the Hua system, to identify exoplanets that could harbor life. The team has mapped known exoplanet systems crossing within the telescope's field of view.